So now let's look at the solutions to problem set 5. And as you may remember, this was something that we primarily deal with enols and enolates in this problem set. So the first question here is that the pK of 2,4-pentane dione is 9. So draw out the equilibrium and reason out the high acidity of this compound when compared with 2-pentanone. Okay, so let's just draw out the structures of these compounds. So this is 2,4-pentane dione, and 2-pentanone would be basically the ketone is present only in position number 2, and the rest of the numbering is the same: 1, 2, 3, 4, 5. Okay, so if you see the pK of the carbonyl compounds, you've already studied this in the past. They range somewhere between 20 and 25, and the most acidic of these would be around 18, 19 or so. So therefore, there's a huge difference in the pK levels of these two compounds. So the question is, draw out the equilibrium and reason this out. So the way we would sort of draw out this equilibrium is in the following manner. So this is the equilibrium arrow, and there would be H plus that is being produced. So you have 2,4-pentane dione, and as you can guess, this is the most acidic proton, and so that's going to get deprotonated and it will form H plus. And clearly the carbanion is not the stable form, and so the carbanion is going to go and form the enolate. And the important thing in this enolate is that the enolate can delocalize further and produce this other enolate over here. And so in effect, you might have seen pictures of this in the following manner. So you would have a dotted line, you have oxygen, and you have a negative charge here, right? So this is the kind of picture that we would draw out for this enolate, and therefore the conjugate base of this acid is highly stabilized. So from our previous discussions, we know that the more stabilized the conjugate base, the better the acid, or we reason out acidity through measuring the stability of the conjugate base. And so here the conjugate base being quite stable, the pK value is quite low, which is 9. Now let's move on to the next question. So the next question here is for the compound shown below. Draw out the tautomer. I think most of you could pretty much get this question very easily. So you have this 2 hydrogens over here. Once the carbonyl compound tautomerizes, it's going to form the enol, and this enol is actually a very special enol, which is commonly known as phenol. And in this enolization process, it has actually gained aromaticity, and we all know that aromatic compounds are substantially more stable than their corresponding olefin counterparts. And so when we try to detect the keto form in this compound, we are unable to detect it using a variety of experimental techniques. So therefore we can propose that the equilibrium constant is really large in favor of the phenol. So the keto form is certainly not the stable form in this case. Now the next question is basically this compound here has 2 signals in the aliphatic region. So therefore if you look at it, these are the aromatic hydrogens as 1, 2, 3, 4, 5, but this is equivalent to this proton is equivalent to this, and this is the third hydrogen. So therefore you would have 3 distinct signals in the aromatic region. Now correspondingly in the aliphatic region, you will have 1, 2, and these 2 signals are the same because they are equivalent. These 2 hydrogens are equivalent, and so you will see the one type of signal for these 2 hydrogens. And these 3 hydrogens again are equivalent, and therefore you would see another set of signals, which is what the question says, is that you would see 2 signals in the aliphatic region. Okay, and now when you dissolve this molecule in D2O, and if you measure the NMR spectrum again, you don't see proton, you don't see any signal for the aliphatic region. And so this is how we would reason this out. So if you imagine that the molecule here has this kind of a structure. So we know that ketones can enolize, but the enol is not as stable as the ketone, and therefore we don't detect it using conventional analytical techniques. And so you can imagine that this hydrogen can be pulled out by water, in this case D2O, and correspondingly when it forms the enolate can again pick up a proton from D2O. And so this is a neutral process, there is no loss or gain of H+, and it forms this tautomer which is shown here. Now when the tautomer reverts to the keto form, it doesn't go back to this form because the dominant, although there is a small amount of, perhaps a small amount of H+ that's floating around, that is basically derived from this, but the majority of the population of the solution is actually D2O, and so therefore when the enol tautomerizes to form the ketone, it actually forms the deuterated ketone, right? And now, as you know, this is an equilibrium, so this is going to go back. If it goes back, it can enolize at the hydrogen or deuterium, but once in a while if it enolizes in the hydrogen, you're going to end up, this process is going to repeat and you're going to get the di-deuterated form, and then all of these hydrogens are going to get replaced by deuterium. So this is the product that you would expect to see in NMR, and therefore you will not see any signal because, as we discussed earlier, deuterium is NMR silent, proton NMR silent, and therefore you don't see a signal for this. So when you add this molecule in D2O, the two aliphatic signals completely disappear. Now the aromatic signals do not disappear because the aromatic hydrogens are not enolizable, and so therefore they remain attached to the carbon and do not dissociate. And so the aromatic signals will continue to be present. Okay, let's move on to the next question. So here, the question here is when the following compound is dissolved in acetonitrile and a catalytic amount of H+ was added, in one compound you found that there was an enol produced, and the other one there is no enol formation. So the way we would address this question is to start with cyclopentanone, and when you add a catalytic amount of H+ in H2O, you can start detecting some level of enol that is being formed, and although it may not be in a very large concentration, but you can detect this. Whereas in the other case, when you attempt to form the enol, although this hydrogen is enolizable, that is, it is next to a carbonyl, once it forms the enol, you actually produce a double bond across a bridgehead, and this clearly is not something that is favored, and in fact there is a rule that sort of suggests that it is not possible, and this is known as the Brett's rule. And so we could suggest that this compound is actually quite unstable and therefore it would not form. So between the two compounds, the cyclopentanone is likely to form the enol, whereas this compound here is unlikely to form the enol. Now moving on to the next question. Here you're given this dicarbonyl compound, and analysis, when you dissolve this in toluene, as toluene is just a solvent, and it shows the disappearance of this compound but the formation of two distinct compounds. And then when we measure the mass spec of these two compounds, we find that it is identical to the starting material, and so that gives you a clue that these two compounds are actually tautomers. And so in principle we could produce two different tautomers, which is shown here. So one is in which this ketone is going to form the enol, and the other one in which the aldehyde is going to form the enol. And so, for example, you can detect this using even conventional techniques such as TLC analysis. You may form two different compounds. You will be able to see this in other techniques as well. So these are what I think are the two compounds that are formed are these two. Now let's move to the next question. We've already discussed this. 2,4-pentane dione exists in solution with its enol form with an equilibrium constant of 4. So calculate the percentage of keto form in solution. Okay, so this solution is fairly straightforward. So if you start with 2,4-pentane dione, if the equilibrium constant is 4, then from the equilibrium constant you know that it's the K equals concentration of product divided by concentration of starting material. So you can do the math, and you would get 80% of the enol form and 20% of the keto form. Now let's move on to the next question. So a new compound whose structure is shown below was being isolated, and mass spectrometry showed the M by Z was 136.05, which is what is expected for the structure. But when you record the NMR spectrum, you would expect a signal between 9 and 10 ppm for the aldehyde, but that was absent. So the question is, what was the compound that was instead being isolated? So given that this proton was absent and the mass is in the, you're trying to make this compound, one possibility is that you may want to consider the possibility of enolization. So let's now look at that option. So when you start with this compound and form the enol, let's say we start with this and the benzene ring is over here. So here is the hydrogen, and so this you can in principle propose that it can form the enol form, and the enol form is going to look something like this, right? Okay, now this is the enol form, and now keep in mind that if this compound, this is the hydrogen over here, just to be clear. So in principle, if you imagine that this carbon-oxygen bond is the enol and this is the enol, this can revert to the carbonyl over here to form this aldehyde. But you notice here on the right, you also have the same CO bond with the same enol configuration. So in principle, you can propose that it would form the keto form, where this carbon-oxygen bond can actually form the keto form. So you would end up with OH, H, and C double bond O, pH, right? So here is the structure of the compound that you can form. And now between this aldehyde and this ketone, the keto form actually is, has some conjugation with the aromatic ring, and you may expect that this is going to be more stable, right? So under the conditions under which you're trying to isolate this compound, it is possible that it forms this enol, which can subsequently produce this ketone. And this ketone may be difficult for it to go back because this itself is quite stable. So therefore, what we would propose as the structure over here would be this, where there's a conjugation with the benzene ring. Let's move on to the next question. So here, the molecular formula of the compound, which is C6H8O2, and through some analysis, it's been found that it contains a cyclohexane ring. And the IR spectrum also shows a distinct signal at around 1700 centimeters and no other significant signals. So design an experiment that will help you identify this compound. Okay, so what we are given is that we are given that there's a cyclohexane ring, and we know that there is two oxygens in the molecule, and it's not O2, but it's two oxygens in the molecule, and we know that there is a C double bond O. Okay. Now, based on this, we can propose that maybe there are two carbonyls. And so if I look at the molecular formula and draw out the various isomers that are possible, so I would get these three compounds. So this would be C6H82468 and O2. So the molecular formula is correct. And now these ketones have very nice arrangement. So this is a 1,2 dicarbonyl compound. This is a 1,3 dicarbonyl compound, and this is a 1,4 dicarbonyl compound. Okay, so this is the difference between these three compounds. And then the question here is that how do you design an experiment that's going to help you distinguish this? So let's consider the first case. This is the favorite case for us because we know very well about 1,3 dicarbonyl compounds. So when you dissolve this in solution, we know that it primarily exists as the enol. So in this case, the pKa has been reported to be 5.24, and this is fairly acidic. So if you put this in solution, it's going to primarily exist as the enol form. And so the enol can be detected using many techniques, including NMR. But if you run a TLC, for example, you would see a clear disappearance of the keto form and to produce the enol form. I'm just drawing the enol here to be a little bit more polar, but that's just a guess. We'll have to do the experiment to actually find out. So therefore, you would see a new peak that's going to be formed. And so if you do see a new peak or a new spot, or if you do an HPLC analysis and you find a new peak, then you may suggest that it is the 1,3-dicarbonyl compound. But we'll have to also rule out the other two possibilities. So when we take the 1,4-dicarbonyl compound, when we dissolve this in solution, we would expect to form this enol over here. But this enol, there is no special reason for this to be stable. So this is very much just like cyclohexanone or even acetone for that matter. Okay, and so when we know about cyclohexanone and acetone, that there's pretty much 0% of the enol being formed, or we're unable to detect it. So if your solution does not produce any new peak in HPLC or does not produce any new spot in TLC, then you can suggest that it's the 1,4-dicarbonyl compound. Now lastly, you can have the 1,2-dicarbonyl compound, and so some studies show that the enol form of this 1,2-dicarbonyl compound, this is the enol form. So once you tautomerize, this is somewhat a little bit more stable than the keto form. So the studies have suggested that this difference is about 1 kilocalorie per mole. So it's not very large. So it is certainly something that will show up in an experiment, but it's not it's not a very large number. So what we can suggest is that in the, let's say, HPLC analysis or TLC analysis in solution, so let's say this is the starting material. So you may still continue to see the starting material in the TLC, but maybe a diminished spot, and you may start seeing a new spot for the enol. Okay. Or if you're doing an HPLC analysis, you may see the peak for the starting ketone, but you'll also see the peak for the ketone and the enol. Okay, so this is something that we can find out using one of these techniques. Okay, so therefore the strategy which we would use is to dissolve this in solution and either do a simple TLC or to see whether there are any new products being formed. So in the case of the 1,2-dicarbonyl compound, which is what we are discussing right now, you may see two spots. One will be the starting material, another would be the new spot. In the case of the 1,4-dicarbonyl compound, we do not expect to see any new peak or new spot. And in the 1,3-dicarbonyl compound, we expect it to completely form a new spot, that is disappearance of the starting material and formation of this new enol. Now let's move on to the last question, to the penultimate question. So here, you need to propose a synthesis for this compound. And so if I look at this compound, you can imagine that this could have derived from cyclopentanone. And the reason being that we know that when you take cyclopentanone and put it in D2O, you're going to get this tetra-deuterated compound over a period of time. And now all I need to do is to convert this ketone into an olefin over here. So the way we would do this is to react this with sodium borohydride to produce this alcohol over here, and then maybe treatment with concentrated H2SO4. You may form the carbocation, which is going to eliminate and produce this product. Okay, so keep in mind here that this is still a hydrogen over here, so we may not replacing that with the deuterium, and so one of these deuteriums might fall off and give you the final product. Okay, so you can imagine many variations for this question, and you can form a variety of products starting from cyclopentanone and D2O. And the last question is about taric acid. It's a natural product. It's found to exist as an enol. Draw out the possible enols and suggest which of these would be the dominant form. Okay, so this is a fairly straightforward question. So you have this hydrogen over here, which is going to enolize. So once it forms the enol, it's going to give you, one of the enols here is this, and the other enol is if it tautomerizes with this carbonyl, it's going to give you enol B. And now of these two structures, enol A with its double bond conjugated to the two carbonyls, so this double bond is conjugated to both these carbonyls, is more stable than enol B, which is conjugated only to this carbonyl. So I would expect that enol A is going to be more stable. The next question is, write the structural formulas corresponding to these three ketones. So let's look at them one by one. The first one is 2,4-dimethyl 3-pentanone. So I'm drawing out the structure of 2,4-dimethyl 3-pentanone over here. And so this is the keto form of this compound. So what we would expect is that this ketone, there are two ionizable hydrogens. So if I number it as 1, 2, 3, 4, 5 carbons, so in carbon number 2 there is a ionizable hydrogen, and carbon number 4 there's an ionizable hydrogen, and either of these hydrogens can be involved in tautomerization or enolization, and you end up with either the enol between carbon 3 and 4 or enol between carbon 2 and 3. Okay, and of course you will very quickly understand and realize that they're actually the same enol. They're identical. So the only basically the only product that is formed, the enol that is formed here, is the one that is shown here. In the next question is acetophenone. So here in acetophenone, there are the benzene ring over here is not involved in enolization because the carbon next to the carbonyl does not have any hydrogens, whereas the methyl group here has three enolizable hydrogens, and so the enol form of acetophenone is actually in this is the enol form of acetophenone. So again, the strategy that we would employ to address these questions is to first identify the enolizable hydrogens and then move on. The third question, or the next question, is that the enolization of 2-methyl cyclopentanone can actually happen in two different places, and so you have this hydrogen, two hydrogens over here, and then there is one hydrogen over here. Let me just draw it out for us to see. So this is one hydrogen, and this is the other hydrogen. If either of these hydrogens can undergo enolization, or it can be involved in enolization, and so if this hydrogen is involved in enolization, you get the product on the right, which is 6-methyl cyclohexene 1-ol. And if the other hydrogen, the green hydrogen or the one next to the methyl group is involved, then you get 2-methyl cyclohexene 1-ol. So the next question is the product from alpha chlorination of R secondary butyl phenyl ketone with chlorine in acetic acid chiral, is it optically active? Okay, so this question can be broken down into two parts. The first part is the identification of this product here, and the second part is the product of alpha chlorination. Okay, so the first thing to do is to write out the structure and then assign the stereochemistry. So my suggestion would be that you spend some time, and once you write the structure out, then you can then assign the stereochemistry as R or S, and then move forward with the R isomer. So let me solve this problem now. So the way this is the structure of R isomer of this compound, and so if I have to look at the stereochemistry, so hydrogen gets the least priority, the carbonyl gets priority number 1, the ethyl group gets priority number 2, and the methyl group gets priority number 3. So this is clockwise the way it's drawn, and therefore it is R stereochemistry. Now what we can sort of propose is that, again, see, if you see from the previous question, we have understood that the benzene ring does not enolize, and so the only enolizable hydrogen here is this one. Now when it enolizes, what is going to happen is you're going to have an equilibrium between the keto form and the enol form, and as you know, the enol form is actually planar. Now if this enol reacts with chlorine, we know that the chlorine reaction with the electrophile can occur from the top face or the bottom face, and they are equally likely, and therefore it is understandable that you will get a mixture, you will get a racemic mixture. So let me explain it in the following way. So once you form the enol, then the attack of the enol to the to chlorine is going to occur in the following manner. So you have OH, and it's going to attack in the following manner to Cl, and chloride ion is going to be lost. Okay, so what is going to happen is that if this is above the face of the olefin, the same reaction can also happen with from below the face of the olefin, and so you'll end up with a 50-50 mixture of R and S forms of the halo compound. Okay, So I would urge you to draw out both these compounds and assign R and S for yourselves. But the product itself, each of the is not optically active because you'll get a racemic mixture. But the two products that are formed are individually chiral. In the next question, we want to understand what are the two most stable enol forms of the following carbonyl compounds. So let's take them one by one. The first one is it's a 1,3 dicarbonyl compound. So if you draw out this aldehyde as shown here, again there are two sets of enolizable hydrogens. There is the CH2 as well as the CH3. But we already have discussed that the enolization of the CH2 is far more acidic compared to the methyl group, and so it's it can form an enol far much more readily than the other methyl group. So now if the aldehyde is involved in the enol formation, then you end up with this kind of a structure. This kind of a structure. And if the ketone is involved in the enolization, then you get this kind of a structure. And they are of comparable stability. In the next problem, again you have a central methylene group which can undergo enolization, and there is a methyl group on the right which clearly can undergo enolization but does not enolize because again our understanding is that the active methylene group in the center is far more reactive or far more acidic than the terminal methyl group. So again you have a choice of two different ketones. So we're just going to write it out here. So this is one of the enol forms where it's conjugated with the benzene ring, and this is the another enol form where it is adjacent to the methyl group. So if we have to suggest which one is more stable, it's likely or it's possible that the one with the conjugation is actually more stable. The next question is, write the structure of the enolate ion derived from each of the following beta dicarbonyl compounds and give the three most stable resonance forms of each enolate. So let's start working on this one by one. The first question is 2-methyl-1,3-cyclopentane dione. So let's look at this answer here. So this is the structure of the cyclopentane dione, and what we can suggest is that hydroxide ion picks up this proton and forms a carbanion, and again we know that the carbanion is likely to resonate with the adjacent carbonyl compounds, and so if one of the resonance forms is the carbanion, then the other two resonance forms as drawn here are actually the enolate forms. So the answer to this question is that these are the resonance forms of the enolate that is going to be formed. Similarly, when you have the 1-phenyl-1,3-butane dione, then you first generate the carbanion as shown here, and that's one of the resonance forms. And the other resonance form is shown here where the where the ketone which is adjacent, which is formed by the methyl group, is actually going to be involved. And the other case is where the benzene ring is involved in the formation of the enolate. So therefore the three most stable resonance forms are as shown here. Lastly, we have a similar question in that we have an aldehyde and a ketone, and again when if you push the arrows, hydroxide ion attacks the hydrogen here and generates the carbanion, and the carbanion is a resonance form of these two enolates as shown here. So I would urge you to draw out each of these structures and convince yourselves that this is the answer to these questions.